Get that out of the way. Okay, so today, like it says right there, changes in matter. You can see there's the date. Again, it's a good thing to put the date down, because if you're going to go back to Google Classroom to do some studying, maybe to watch the movie, you can always go back and find that date. So today's is about changes. And the first one we're going to talk about is a physical change, and I really dislike the animations. But anyway, a physical change. So there's two types of changes. Just like we can have physical properties and chemical properties, we can have physical changes and chemical changes. All right? So there's two types of changes. In a physical change, nothing new is created. The substance is the same. The only change is in its form. All right, so it's maybe taking on another form. There's no rearrangement of the atoms. The atoms are staying in the same positions. Now, on the next slide is a graphic that's going to describe a group of physical changes that you're all acquainted with. But I'm actually going to write it on the smartboard, because I really don't like the way it's kind of drawn there. So a very important type of physical change is, and I'm just going to put here example, change of state. Change of the physical state, solid, liquid, and gas. All right? You've done that type of thing before, right? Changes of state, yep. What's the fourth state? Excellent. That is another state of matter. We're not going to be dealing with that in this course. There's actually a fifth state. There's something called a Bose-Einstein condensate. We're not going to be talking about that either. These are states of matter that exist often in high pressure, low temperature, all kinds of specialized situations. Let's just stick with our classics. But thank you for the information. So just to remind ourselves of the change of state, I like to put my changes of state in a row up and down. Lots of graphics and textbooks like to have the changes of state in a triangular thing, but I like to have mine as up and down, and there's a reason for that. I like to start with the highest state, gas, right up here, and I do want you to write this down. And then down below that, I'm going to put here, well, what am I going to put next, do you think? Liquid, and then solid. There's a reason I like to put it in that order, and it has to do with energy. All right. The only difference between the states is how much energy each of the little particles have. In a solid, there's not a lot of energy in the particles. If I have a cube of ice, all of the water molecules are sitting nicely in a row, kind of like the way you're sitting right now. If you were to be, representing molecules in a state of matter, right now you'd be representing molecules in a solid, because you're all sitting nice in a row. And that's what a solid is. Everything's sitting nice in a row. And then when you go up, right, and you go to higher energy, then the particles are able to move more freely. So when you add energy, the particles are able to move around a little more. What do we call it when a solid becomes a liquid? What do we call it when a solid, we're going to give some other people a chance here. What do we call it when a solid becomes a liquid? Ice becomes water. What's it called? Yep, melting. Melting. An example of, melting, ice becomes water. If you guys are pretending to be in a solid state right now, the representation of you melting would be like when the bell goes. What happens to you guys in your nice orderly state when the bell goes? You get up and you start moving around. You start moving around. Here, you guys are gaining some energy. You're becoming a liquid. Go ahead and become a liquid. They're moving out of their orderly state. This is too many becoming a liquid. I don't like this. Too much melting going on here. And notice how they can flow out the door. Okay? So that's why I like to put them in order. All right? So what happens the other way? Oh, they moved my stinking cart. Who bumped it? Killing me here. Ignore that. I'll use that line later on. What is it called when the liquid then goes back to being the solid? Yep. Solidification. Freezing would be fine. I'd be okay with that. Solidification or freezing. To freeze. All right? That means it's got to give up some of its energy. When these guys come back and they're using up all their energy, they're going to come back down, they're going to sit back down, and they're going to give up that energy. They're going to lock back into place. Okay? Excellent. Liquids, if the particles get even more energy, those particles can jump right out of the glass. Those particles can leave the glass and become a gas. What do we call it when a liquid becomes a gas? What's our term? Evaporation or vaporization. Evaporation is kind of a special one that takes place below the boiling point, right? And like a puddle evaporates. But if I were boiling water to make some KD, right, or something like that, we wouldn't say evaporating anymore. So I'm going to use vaporization. Vaporization. And I pardon for squeezing that in. Vapor, A-O-U-R-I-Z-A-T-I-O-N, vaporization. So when you heat something up or something gains in energy, then the particles have all kinds of energy and it vaporizes and they can go wherever they want at that point. We can take our example of you guys right now being like a solid, and then when the bell goes, you guys move into the hallway and move around and become a liquid. What would be an example of you guys becoming a gas? Yep. Leaving the school and going wherever, uptown, right? A solid is confined to its spot. A liquid is confined to its container, like the school, and a gas can leave the container, going out, going downtown, going wherever you go. At the end of the school day, everybody evaporates or vaporizes away. Okay? All right? The reason I like to put it in this step has to do with its energy. Solids don't have a lot of energy in them. That's why they've got to be cold. Gases have lots of energy in them. That's why they have to be hot in order for this to happen. In order to go from a gas back to a liquid, what is it called? Yep. You could maybe use that term. That's not the term I like using. There's one that's a little more common. What do you call it when you're taking a hot shower, you get out of the hot shower and the glass becomes all foggy? What has happened on that glass where that liquid has landed on there? Condensation. Condensation. All right? Now, I do need to put two big arrows that go that way, right? And then that also go that way. And that's what makes kind of this picture a little goofy. And there's my funny line right there. Going from a solid to a gas. Yep. No. It's a weird word. Starts with the letter S. You may have heard it before. It's called sublimation. Sublimation. So going up this way is sublimation. All right? Now, I remember years ago I was taught that going the other way is also called sublimation. Okay? But new books that I've heard, they've changed the name, and they've got here, going from a gas to a solid, deposition, deposition, to deposit onto something. So we'll call that deposition. Deposition. To deposit the solid onto something. This happens when the weather gets really cold and it's like below zero outside, and you might leave your car outside. If there's some water vapor, if there's some water humidity in the air, where does that end up in terms of your car in the morning? And what does it look like? What do we call it? Frost. Frost on a windshield is deposition. Okay? So, changes of state. The reason it's a physical change is because when all these changes happen, the particles stay the same. When you go from sitting in nice orderly rows in the classroom to when the bell goes into the hall to when the day ends and you leave the school, you're still the same person. You're not being turned into something else. When water that is in ice goes from a solid to a liquid because the particles move around, their particles are still H2O, just like they were when they were in the ice. And therefore, it's a physical change. In physical changes, the particles don't change. They stay the same. Let's look at a few more different types of changes here. So there's the change of state grid. That's great. We've got that. So change of state, we already have that. Let's take a look. Oh, I'm not going to worry about that. Oh, stop. Dissolving. So write down also underneath the changes of state, dissolving of a solute into a solvent. I'm going to freeze that right there because I don't want you to be distracted by it. We'll look at the video here in a moment. So another example is dissolving of a solute into a solvent. When a substance dissolves, like sugar or salt, it doesn't turn into anything new. It's still sugar. The same molecules are the same, it's just in the water. How do you know that the sugar is the same when it's in the water than when it's in the solid? You all have an answer to this. How do you know? You've never tasted sugar? Yes, you've all tasted sugar. Abundant amounts of sugar. What happens if you lick like a sugar cube? How does it taste? And what word do we use to describe? It tastes sweet. What if you put some sugar in some water and you taste the water? How does it taste? You've never done it? It still tastes sweet. And that's because the molecules are exactly the same. The same molecules are activating your tongue, the same ones, and your tongue is telling your brain that's sweet. So when something dissolves, it doesn't change. All right, let me disconnect this. Don't worry about this conductivity probe. We'll look at that later on. What I want you to look at in this particular little animation is what's happening to the sugar molecules. So here we've got some sugar. We're going to zoom in as if we could somehow do that. And these big C12H22O11, they are each a sugar molecule. It's got a lot of atoms in it. And you can see these little things. These are water molecules. The yellow dots are H's, and the red dot is an O. And you can see the water molecules are taking the sugar molecules away. That's the dissolving process. But notice how the sugar molecules aren't changing themselves. They're staying the same, which means dissolving is a physical change. Nothing new is being formed. Yep. Mixing, what do you mean mixing? No, it doesn't. It's not attaching with a chemical bond. It's being attracted to it, kind of like how a container. Don't mind this guy. That's just my last guy. Ignore that guy. I shouldn't have distracted you with the laughy guy. The question was, if the water is sticking to the sugar, is the sugar not becoming a new thing? That's what your question is, correct? Sugar with water on it. Okay. The water, when it's getting close to the sugar molecules, isn't chemically combining with it. It's just attracted to it. The water molecules have a property where they behave a little bit like magnets. They're not magnets, but they behave like magnets. I have a container of magnets and ball bearings here for demonstration purposes. And this container is just a whole bunch of magnets and ball bearings together. You can see that. We could imagine that the magnets are like the water molecules and the ball bearings are like the sugar. But just by sticking a ball bearing to a magnet, I don't change the ball bearing itself. It's just attracted to it, okay? And that's what's happening to the sugar and the water. The water is just attracting to the sugar molecule to pull it into the water. It's not physically held together. Sorry, it's not chemically held together. They don't become one chemical thing. They're still their own entity. You can separate it. You could boil off the water and get the sugar back. You see what I mean? And it wouldn't need some kind of chemical means. I just need to heat it. So it's just pulling them apart. It's not turning into a new substance. So it's a good question. So a chemical change. Let's write that down. A chemical change is a different thing. When a chemical change happens, completely new things are formed. Their atoms change positions and become new things. The rusting of iron. You start with nice clean iron, it rains on it, it gets wet, oxygen gets it, it attacks it, and we now have a completely different substance. Yep? Yes, it would be. It would be a chemical change. It would be reacting with the air. Correct. Yes. Burning paper. Correct. Our zinc and our sulfur yesterday, right? We started with certain properties. We chemically changed them into completely new things. Yep. Yeah, that's related to rust. All right. Many metals will react with oxygen. Yes, that's the same thing. It's a copper oxide. It's an oxide of copper. We save the term rusting for just iron. In the chemical world, when we say something is rusting, it can only be iron. We don't say that the copper rusts. We say it corrodes. But rusting is an example of corrosion. It's the same chemical process. Burning of a fuel. All right, you can write that down. That's like burning paper, burning of a fuel. This is a video of burning sugar. We can dissolve sugar, but we can burn sugar. And this is a reaction where we put it in with a very high oxygen source. Remember we talked about oxidizers when we talked about safety stuff? I have an oxidizer. I actually have it in the other room. And I actually have a gummy bear. And we could burn that. And we could get it to combust. And I'm going to show you that. I didn't check the link to the video. I don't know if this video is going to show. Let me just see what the next thing is. I'm just looking at the time. I want to make sure we get time. We won't talk about the video. We'll actually go and burn a gummy bear here in a moment, okay? Okay. So this is a longer little note here. We've got to put this. How do we know if a chemical change takes place? Brett, where's your notebook? No, that's your lab book. You put lab information in your lab book. You're going to put note information in your notebook. Does that make sense? Okay? Because I don't want to fill your lab book with notes because we need it for labs. Okay? All right? So, how do we know whether a chemical change has taken place? Well, there's evidence that tends to always be around when a chemical change happens. So we're going to have one or more of these observations present itself when a chemical change takes place. Number one, a gas can be produced. It doesn't have to be, but it can be. A gas can be produced. Did anybody see any fizzing or bubbles in that last experiment we did? Did we see the fizzing in the bubbles? Chemical change was taking place. A change in color. We actually saw some chemical reactions in that last lab. We saw some color changes, I assume. Some phenolphthalein might have changed some color, right? Became purple, I think. Formation of a solid. Sometimes a new solid can be formed. When we saw the zinc and the sulfur react together, we started with a powder that was yellow and a powder that was gray. And then when we allowed the reaction to happen, we had a powder that was white and had a little bit of yellowy color to it. But it became white. So a change in color. A change in temperature. Typically, chemical reactions give off energy. That zinc reaction that we saw the other day gave off a lot of energy. I don't know if you recall the sparks and the heat and all that good stuff there. Lots of energy given off. So it got really hot. Sometimes light is produced. Not always, but sometimes. Light can be produced. Don't send messages.
I'm actually going on 5.
Are you?
Yeah.
Oh, okay. That's okay. It's just you looked at your phone and then you had a smile on your face and did it okay because my notes are not usually smile inducing. They usually make students frown. So if you look at your device and you go, you're not looking at my notes. Light is not always produced. If something is really hot, light can be produced. We can actually have light produced sometimes in a chemical reaction that doesn't get hot. If you've ever had one of those glow sticks, we all know the glow sticks, right? You know, break whatever's in there, give it a shake. You know what I'm talking about, the glow sticks? What you're doing is when you're bending that, there's a little capsule made of glass that contains one of the chemicals. On the outside, on the plastic, not on the outside, but inside there's the other chemical. When you break the glass on the inside, you allow the chemicals to mix. When you give it a good shake, you're really mixing the chemicals up. Those particular reactants produce light energy and it glows. All right? It doesn't get hot, but it gives off light. So some chemical reactions can give off light without getting hot. And that indicates a chemical change. Formation of a new substance with different properties from the starting ones. That's like a new solid, or maybe a new gas, or perhaps it's still a solid, it just looks different. Like in the zinc and sulfur example. They're all solids. We started with solids, we ended with solids. But in the end, the solid looked completely different. It had completely different properties. So when we have these physical changes take place, so we can see these physical properties that are changing greatly, like a new color is formed and it gets hotter or gives off light, or a new solid is formed, we've had a chemical change. It's turned into something new, and we're not gonna be getting back the original stuff. Not very easily anyway. Now, there's a few of you that came in a little late. You're writing like crazy, and that's awesome. I'm freezing the slide here. I just want to see what I've got next. All right, so my next slide is on gas tests. You guys might have did gas tests last year. Did you do gas tests last year to test for gases? Some of you might have, some not. I'm going to save that for tomorrow. Actually, what's going to happen here in a moment, and I'm actually going to stop my video here.